Okay, so I'll just pick up with one more concentration inequality and then an application to Monte Carlo integration, and then we'll go into some stuff on graph-based learning. So this is one of the most useful concentration inequalities, and basically these ideas sort of subsume everything else that I talked about before. Okay? So here we're not looking at a sum of random variables, but a function of a sequence of random variables. Okay. So the x1 through xn are IID. Okay. And essentially we'll prove the exact same concentration of measure results as long as f doesn't depend too much on any one of the entries. Okay. And these are very general and very useful results. So we assume the bounded differences condition. Which means there exists some parameter b, some number b, such that if I take, just like Adam wrote yesterday, if I take x1 through xn, just any numbers, and I change xi to be something else, xi tilde, that the change in f is no more than b. So let's say xi tilde. This holds for all xi, x1 through xn, and for xi tilde, and for any I that you choose. Okay, and there was a question, I think, if this is a Lipschitz bound. It's not, as far as I'm concerned, a Lipschitz estimate, but this is what people call it in the textbooks, actually. So if you look at the probability textbooks, they say we assume a Lipschitz condition here. Okay.
It's in some sense, especially if the xi's are a finite number of variables, right? I mean, it's symmetrical number. And imagine your xi's are signs.
If they're signs, yeah. But most of the time, you're not talking about discrete domains, let's say. So anyway, it's also called bounded differences, which is what I like to call it too. Okay, so the amazing thing is that you can prove essentially the same concentration and measure result. So this is I'm calling it Azuma McDiarmid, which is what you see in textbooks a lot. So again, we're going to assume, essentially we just have this set up here. And for every positive t, maybe assume that we have bounded random variables as well. So it doesn't come into it, but I think we should stay on a compact set. Okay. So for every positive t, probability that yn minus expectation of yn bigger than t goes like exponential of minus nt squared over 2b squared. Okay. There's a bit of a difference because the way I've written this condition, if this was an average, there would be a divided by n showing up over here. And this is the way it's often written, is you just leave that out. And so you end up with maybe, okay, this actually might be down here. C2nb squared. We'll see when I prove the result, but I think it looks like this. Sorry, t squared. And so the reason I call it Azuma McDiarmid is that really it follows from Azuma, which is something you prove for Martingales. So this holds for sub and super Martingales. And it's a more general result. And when you write it down, you write down an application of it to this thing called the Doop Martingale, and you get McDiarmid from this. So let me just sketch the proof. Okay, so how do you do this, right? You don't have a sum structure anymore. So it seems like all the things that we did before go out the window, but you sort of rescue this by writing down this thing called the Doop Martingale. So this is which is a very simple thing. You look at, let's call it, well, I won't give it a name because I'm going to define this to be something else later. So if I take expectation of yn, I condition on the first k random variables, okay? And treat this as a sequence indexed by k. This is a Martingale, okay? I won't define a Martingale, but you can trust me. This is a Martingale, and it's called the Doop Martingale, okay? And then you apply Azuma to this Martingale and you're done. But I haven't proved this to you yet. So let's go through the proof, which is basically the proof of Azuma for this Martingale. So you look at the Martingale difference sequence. Okay, so this is the difference between this conditional expectation and the previous one for k minus 1. And let me just say maybe a word about conditional expectation in case you have not seen this before. You should think of this as you're freezing these random variables, and it's the expectation over the rest of them. Okay? And so this is actually this itself is a random variable, which is a function of x1 through xk. Okay? And it's like the best mean squared estimate of yn that's a function of these random variables. And so what I'm doing here is I'm saying, how does the expectation change if I add the information from one of the random variables, xk? Okay. And I'm going to just add this up over the whole, from k is 1 to n. So this is zk. If k is equal to 1, I have no conditioning. So z sub 1 is expectation of yn given x1 minus expectation of yn. Okay. And just to note that if I condition on everything, it's just yn. Okay. So actually, I have a telescoping sum for yn minus its mean. So I have yn minus the mean is sum, k is 1 to n, zk. Okay, just by definition of these things. And I'm going to treat this like a sum of IID random variables and apply the same arguments we did before. That's the general idea. Okay? And these zk's, sorry?
Where's the difference going? Z n should be minus conditioning on n minus 1.
These are the variables zk. Right? You mean this up here?
Yeah.
If you condition on everything, there's no expectation anymore. So remember, you should think of it as the expectation over the other random variables that are not being conditioned on.
But there you're subtracting the previous one.
Yeah. Yeah.
So by that definition, Z n would be minus, right?
This is sorry, I meant just this. Sorry. Sorry. Thank you. Yeah. So this is just a telescoping sum like this. And these zk's are called the Martingale difference sequence. Okay, so how do you prove this? Well, you just go through the exact same Chernoff bounding trick. Okay? And there are a couple of steps that are a bit different along the way. So we're going to say probability that yn minus expectation yn. So it's the same thing. I'm going to multiply both sides by s. This is bigger than t. I'm going to multiply both sides by s and exponentiate, so it's e to the s yn minus expectation. Okay, and I'm going to write this out as a sum, and I'm going to apply Markov. Right? Okay. So by Markov, I get the e to the minus st, and I get expectation of this random variable. And here I'm going to write the sum of the zk's now. Okay. So that so far is basically the same that we had before. Now, two things to prove about zk that that maybe I'll leave as a short exercise. The first one is easy, which is that expectation of zk given x1 through x k minus 1 is equal to 0. Okay? So there's 0 mean if you condition on x1 through xk minus 1. The point is that when you condition on that, it's like you remove the xk from here, and it's the difference of two things that are equal. Okay? So this is like a mean 0 condition. And the second is that the bounded differences condition implies that the zk's are almost surely bounded by b. Okay? Because essentially all I'm changing here is whether or not I fix xk. Okay, so I have the expectation over xk over here, and here xk is fixed. But when I change the kth coordinate, I can change f only by at most b. Okay, so it's a 3-line exercise to write this down. So given these two things, okay, now I'm going to do the Azuma trick. So yn minus expectation, yn. Okay, so the point is, this is less than what I have here, e to the minus st. Now I'm going to use the law of total expectation, or conditional expectation, right? Which is that I can condition on whatever I like and take an outer expectation and I get the same thing. Okay? So it's the expectation of this e to the s. K is 1 to n, zk. I'm going to condition on everything except for xn inside here. So if I condition and then take the expectation outside, it removes the conditioning. This is the law of conditional expectation, or iterated expectation. It depends which language you like. Okay. xn minus 1, sorry. This is xn minus 1. You can put whatever you like here in the law of conditional expectation. And now the other property of conditional expectation is that anything in here that's a function of these random variables is really a constant for the expectation. And I can pull it outside of the expectation. Okay? And so the zk's, everything except for zn, okay, is a function of these guys. Because they have conditioning only on those random variables or a subset of those. Okay? So I can write this as e to the minus st. I can pull out e to the s. Sum k is 1 to n minus 1, zk, and then expectation e to the s zn, conditioned on x1 through xn minus 1. Okay. And this is the kind of thing I'm going to use the Hoeffding lemma I had before to bound this. Okay? It's essentially the same thing. It's the moment generating function for the random variable zn, conditioned on all these guys. Okay? So to bound this, right, we're going to have expectation of e to the s zn given x1 through xn minus 1. Okay. We use the same trick, right? Because the zk's are all less than b. So I can use the same trick, and if I remember the formula for the secant line, it's e to the minus b times s, right? Minus b times s plus zn minus or plus b over b hyperbolic sine of s times b, right? Conditioned on x1 and minus 1. So remember, this was the secant line of that function. E to the, here it's s times x. I go from minus b to plus b. Okay. And when I bring this inside, the expectation of zn given x1 through xn minus 1 is 0. So I have the mean 0 condition. And so again, that term drops out. And the b over b drops out, and I get the same thing as before, e to the minus of bs plus hyperbolic sine of s times b, and that's hyperbolic cosine, which is less than e to the s squared b squared over 2. Okay. So I can use, this is the Hoeffding lemma, right? I can use that to bound this term, and I can just pull it outside now, right? So now I have, people can see over here. Maybe I can't move that very easily. Okay. Let's write that. E to the minus st. Let's write it as exponential. So I get minus st plus s squared b squared over 2, and then times expectation of e to the s sum of zk. K is 1 to n minus 1. That's it. Okay. So now I just iterate, right? So it's the exact same argument I can apply inductively. I can pop out for every zk, I can pop out an e to the s squared b squared over 2. So in the end, I get probability yn minus expectation of yn is bigger than t is less than exponential minus st. I get n copies, and it was s squared b squared over 2. So it's n times s squared b squared over 2. Okay. And again, what do we get if we optimize over s? You get minus t, or you get t is equal to nsb, right? B squared, thank you. Yeah. And then this means that s is equal to t over nb squared. Okay. And if you plug it in, you're going to get minus t squared over nb squared plus a half of that. And you get exactly this, e to the minus squared over 2nb squared. And the reason it's 1 over n is because I didn't put the n inside the bounded differences condition. If you do, you get what you had for Hoeffding before with the n up here. Okay. But this idea, right, this idea of doing this swapping trick to swap out xi for xi tilde, this is a very general idea that's used in all of, lots of different probability fields and in the stochastic homogenization I talked about for PDEs. This idea of swapping out a piece of randomness to get concentration is a very, very useful general idea.
Where you mean this trick?
It's just this, getting this bound here and then this trick. Yeah, it's pretty simple in the end, right?
Clever. I mean, they must have discovered some other one first.
I don't know the history so well, yeah.
I mean, the tricks, they just come together and start to...
Yeah. Right.
I mean, who would have thought to try it? Wow.
Yeah. Sorry?
How old is this?
This is a good question. I don't know the answer. I mean, I'm not a probabilist, right? So I think about these things in different ways than probabilists do, I think, as well. But I think it's rather, I mean, at least like the Chernoff bounds in Hoeffding. So I think I know there's a paper by Bernstein like in the 20s or 30s where the Bernstein bounds first came about. I'm not sure about Azuma. Maybe this is later. I'm not sure though. Yeah.
So you didn't need this xi less than n.
Yeah, I guess in my notes I was thinking, well, yeah. When you want to prove this, the way I proved it in my notes, I took a supremum over some variables and I wanted a compact set. But maybe you don't need it either, right? So, okay, so I just want to give I was going to give an example to Monte Carlo integration, but maybe just let me say it very, very briefly. Because I want to have time to do the graph-based learning stuff as well. So this is just a very basic application of Monte Carlo methods is to compute something as simple as the integral of a function over a box. Say u of x dx. Where the dimension is large, let's say, okay? So we're going to replace this by some approximation, so call that I of u. Replace it by an approximation, In of u, which is the average over some points. Okay, where these x1 through xn are some points that you decide to place in the box somewhere. Okay. If you are naive and choose them to be a grid, let's say, so if I take, if xi are a uniform grid, that means that the grid spacing, right, if I have a grid in n dimensions, right, what is the grid spacing? It's 1 over n to the 1 over dimension, right, along each direction. Because basically I'll have what? Number of points is going to be 1 over this in each direction, then to the power d gives me the n points. Okay. And if you just take those to be a grid, and this is a Lipschitz function, let's say, the best error estimates you're going to hope for are that I n of u, and this is easy to prove then, is that I n of u minus I of u is less than a constant times delta x. Because it's Lipschitz, it varies by at most delta x within each cell. And this is c over n to the 1 over d. And this is what we call the curse of dimensionality. Right. When d is very large, this is essentially order 1. This is a terrible estimate. Right. Now the point is that this is entirely fixed if you just take the points to be random instead of taking them to be a grid. Okay? It's a simple idea again, right? But if I take the xi's to be IID random variables, suddenly I beat the curse of dimensionality. So take, if they're IID random variables, and just take them to be uniform on the box, then this is less than essentially the variance, which I'll define in a second, over square root n times lambda with probability at least 1 minus 2 exponential of minus lambda squared over 4. And let me say that maybe there's an upper bound on lambda that looks like sigma squared n or something, maybe like an infinity norm of u. I forget exactly, but you can see it in my notes if you like. But you don't take lambda too large, but really you want lambda to be order 1 or to be, just a bit bigger than order 1, so this is a small probability. Okay? And the point is that this estimate, it beats the curse of dimensionality because it's 1 over square root n, independent of dimension. Okay? And you don't see dimension anywhere in here, except maybe in the variance. Okay? This sigma squared is the variance of uxi. Okay, so this is, the first time you see this is quite amazing, right? You can go from curse of dimensionality to beating it just by making your life easier, making random points instead of choosing points to be on a grid or something. And this is just a straightforward application of Bernstein. Okay, so we use Bernstein. And here, okay, so here, these are my random variables I'm going to apply Bernstein to. So the mean is expectation of u of xi, which is exactly the integral to the d. Yeah. And the variance is and if you want to write it out, you can. It's just integral over the box of u of x minus its mean squared. And then you want to get a bound for uxi minus its mean, right? This is what we call b in the Bernstein bounds. And okay, this is just can be bounded by 2 times the infinity norm of u. Okay. That's what I use for B, Bernstein's bound. So now apply Bernstein, and you get probability that IN minus I is bigger than T. Looks like, well, now I have to do the bound in both directions. I'm taking absolute values now. So the bound in the other direction is the same kind of proof. I have to union bound twice, so I get a 2 exponential of minus nt squared over 2, and I get the variance plus bt over 3. Right? And now what you usually do is say, let's take t to be what I had here, sigma lambda over root n. And then the lambda is now the parameter, just to make things better. So this gives me probability bigger than sigma lambda over root n. And here, when I plug it in, t squared, the n's will cancel out. I'll get a lambda squared. I'll get a sigma squared, right? And now you place an upper bound on b times t that depends on sigma squared, and all the sigma squareds drop out. Okay, and that's the bound I was going to write down somewhere. Maybe this is, yeah, on, oh, sorry, this t becomes sigma lambda over root n, right? Okay, and you say the easiest bound you can write down is that that's all less than sigma. So the b, b times lambda over 3 root n is less than sigma. So if you just restrict lambda like this, then you can just drop all the sigma squareds. You get a nice estimate like that. It's just it's a very, very coarse upper bound for lambda. Yeah. So lambda is less than something times that looks like root n, and you want lambda to be very, very small, maybe like log n or something. Okay, great. That's the last part of the concentration of measure. Are there questions about this? Yeah. Which constant? This one over here? This one depends on dimension. It would be like square root of d, maybe? Like the diameter of the box of each cell. So the diameter of the cell will be delta x times root d. So the constant c would be root d times Lipschitz constant of u or something like this, right? Yeah.
It's interesting that sigma squared is the variance of the samples, which is good.
It's the variance of u applied to the samples, yeah.
So you really have an estimate.
Yeah.
You don't need to have the variance of u. I would have thought maybe you need to know how much u oscillates, but you're only.
Well, that's what the variance is. It's how much u oscillates, right?
But is it just the sample variance or the true variance?
It's the true variance, yeah.
Oh, okay.
Yeah.
Okay.
Yeah.
That makes more sense.
Yeah. Okay.
You don't necessarily know that.
I don't know. I mean, maybe you do, maybe you don't. I mean, this is why people look for variance reduction in Monte Carlo, because this is the only thing that shows up in your estimate. It's just the variance of this thing. Right? So if you can convert the problem into a different integral with a much smaller variance that you can get your integral from with a computation or something, maybe that speeds things up, right? Yeah. And of course, this is a extremely simple application of Monte Carlo, but this has been generalized to lots of different problems, like solving elliptic PDEs, where you have like a Brownian motion interpretation of the equation. You can sample Brownian motion paths and get Monte Carlo estimates. And these things are all most of these things, they beat the curse of dimensionality by the same kinds of arguments.
But still, if you inference is uniformly bounded, right? And you have a uniform bound for the scale.
Sure. I mean, so we like the loose upper bound you can put is that the variance is like less than, something 2 times infinity norm squared or something like this or whatever, right? But maybe it's even smaller. So this is just a loose upper bound. Yeah. Sorry?
For this Lipschitz,
You could use Poincaré or something, right? Yeah.
So independent order variance.
Azuma was more like it was like Hoeffding. Azuma is like the extension of Hoeffding to Martingales. There is a Bernstein version for Martingales too, if you want to use the variance of the increment zk instead of just the absolute bound. Yeah. And if you look in my notes and look at the references I give, there are massive textbooks written on these concentration inequalities, and there are like probably hundreds of other variants in different conditions and so on. Lots of them have the same kinds of proofs. I can't claim that all of them do, but. All right. Okay, so in the next 45 minutes, I guess I'll just give a little introduction to graph-based learning and the kinds of analysis that you can do with the concentration and measure results. And this will sort of lead into Dan Slepchev's talks tomorrow, which will be on continuum limits for graph-based learning using variational interpretations like gamma convergence and these TLP spaces that he's developed. Okay, so I talked a tiny bit about this on Monday, if you were at the talk Monday. So let me just review briefly, is that you have a graph, which is your representation of your data. And a graph is a set of nodes x, okay, and edge weights w. So I'll write x as, it's a set of points. Oftentimes they're in RD, but they can just be abstract graphs as well. And the weights, think of it for now as like a weight matrix on the whole graph. Okay, and so this could be, if the weights are 0, right, there's no edge. And a large weight means things are similar. So say around 1 means that x and y are similar. You can construct graphs in lots of different ways, and I'll write down later how we constructed for analysis, which is the random geometric graph. But in general, someone could just give you a graph and ask you to do a learning problem, like propagate labels on the graph. Okay. So the semi-supervised learning problem okay, so here you have, say, k different classes. And these are represented by the standard basis vectors E1 through Ek. So the basis vector Ei represents the ith class. Okay. And you have some subset of labeled nodes in the graph, call it gamma. Okay. And you have corresponding labels. So you have a function on gamma into Rk. Actually, it maps into the standard basis vectors. But in general, we don't. It's not so important for the analysis. And so what you can think is that maybe this is like a social media network. And so each node is like a user. And you construct some notion of distance between the users by how many friends they have in common or something. You cook up something that measures how similar two people are. And now you want to make predictions. So maybe who these people voted for in the election. You want to predict who the other people voted for based on who their friends voted for, right? Or predict what kind of advertisements to show them or something. In the examples I showed on the first day with image classification, it's each data point in the data set is an actual image with all these RGB pixels. And you assign a label based on what class it is. So it's a 0, 1, 2, up to a 9 if it's optical character recognition. And you provide the labels for some of the images. You construct the graph by looking at either pixel differences or some feature differences between images. And then you try to propagate labels on this graph in some way. So the task is propagate or learn, whatever this means, the labels on the other data points in some reasonable way. It's just, as you write it down like this, it's an ill-posed problem, right? There's no unique way to extend these labels, so what do you mean by learn or propagate? And so if you read the textbooks on this, they take the semi-supervised smoothness assumption, which is that they ask that the label function that you learn on the rest of the graph, it should be the smoothest, it should be smooth in high density regions of the graph, okay? And extend the labels. Okay? So labels should vary smoothly in dense regions of the graph. Of the graph or of the data. Okay. So you don't want to say smoothly everywhere, because if you have some outliers or some sparse data, sparse area, you want to allow the label to change rapidly in these areas, but it should be changing smoothly if you're within clusters or something. This is still some heuristic, but so one of the oldest ways to implement this is this Laplacian learning by Zhu and Graham and Lafferty in 2003. Where they said, essentially, let's propagate labels by, you can think of it as harmonic extension or minimizing the Dirichlet energy on the graph. Okay, so you solve the problem, minimize sum over x and y, the weight from x to y, ux minus uy squared, subject to u is equal to g on the set gamma. Okay. And you just minimize over all functions on the graph. X into RK. So this is the variational point of view. Say 1. 2, okay, you can take a gradient of this thing, set it equal to 0. And I don't know how much time we have to go over too much of this stuff, so I'll start going a little faster. Is that this is equivalent to a harmonic extension, so x in x minus gamma, and u is equal to g for x in gamma. Okay. And this is the graph Laplacian, Lu of x is sum of y in x, wxy, u of y minus u of x. And everything is still vector valued. So these are functions in RK. This is the norm of the difference, and this is a vector valued graph Laplacian. So, but you should think really this is like a diagonal operator. So you're not seeing interactions between different components. You still have maximum principal and things like this. So there's the variational perspective, and there's the PDE perspective. And there's also what's important is the random walk perspective on this. Okay, so I can take a random walk on the graph. So let this be a random walk. On the graph with the usual transition probabilities that if I'm at x at step k minus 1, and I want to know what's the probability of going to y, it's the weight from x to y divided by the degree of the node x. Okay. So this is the degree, which is the sum of all the edge weights attached to this. In this talk right now, everything is a symmetric graph. Wxy is equal to wyx, but you can have non-symmetric graphs if you have directed graphs, like the graph that represents the internet, and you have connections from web page x to y, but not from y to x, let's say. Okay. But here, everything is symmetric. Okay, so this is a random walk on the graph. And then what one checks is that if I have a harmonic function on the graph, it's a martingale along the walk, okay? Which means that it has nice averaging properties, and in particular, the solution to this problem is over here, is the expectation of the label that you first hit, given that you start at x. Did I start at 1 or at 0? I don't know. Okay, where t is the first time that you hit a labeled node. Okay. And I think all three interpretations are important. Okay, so it's the first two have gotten more attention recently, and so the first interpretation is where you can use gamma convergence. And tomorrow, Dan Slepchev will talk about these tools, which use energies and variational tools to prove that these discrete problems converge to continuum counterparts. Okay. You can use the PDE point of view to do this as well. So here, if you have a Laplace equation, you have the maximum principle, which gives you this really strong stability, and you can use this to prove convergence. You get better rates than with variational convergence when you look at PDEs. But you can use the random walk point of view to prove these same kinds of convergence results. And we've only sort of realized this recently, and these have been very, very useful tools. So the kind of things that you want to understand are, if I have a very large amount of data in the graph, what's sort of going on in these problems? Okay, so this is just one area in graph-based learning, semi-supervised learning. There's also clustering problems. You can ask, how do I group the data without using any label information? And you have graph cuts, and you have graph total variation. And I could talk at no end about these kind of things, but with half an hour left, I think I'll talk about the consistency results and maybe discrete to continuum with like the PDE point of view.
The random walk only works with power 2 on.
Or if you have, say, P Laplacian, where you look at like the game theoretic P Laplacian, you have these two-player tug-of-war games, which have the same kind of analysis. Yeah. But you're right. So this is, I think the PDE and variational arguments are more general in the sense that you give me a nonlinear PDE in the graph. I can probably use either one, depends if there's a variational principle or not, right? Yeah. So we're sort of interested in like big data limits. And so here we take a model, which is the random geometric graph. And you can take other models, but this is the easiest one to start with, which is where these random variables, or these vertices in the graph, are IID random variables. With a density, say it could just be like a smooth density rho, on, let's say, a set in RD. An open bounded set with a smooth boundary. You can also take the manifold assumption, I should mention. Which is where basically omega is a manifold of smaller dimension embedded in RD, and the density is essentially the density with respect to the volume form on that manifold. Okay? And this is what people in machine learning think that, even if data is presented in high dimensional spaces, it's probably approximated better by a low dimensional smooth manifold. Okay? So most of what I say goes through in this manifold setting, but there's just additional technical details to make this work. So we're just going to sit in the flat setting with a bounded domain. Okay, so now you define the weights. You choose a kernel eta. Okay, say a function from 0 infinity to 0 infinity. We'll say that it's positive at 0. It's maybe decreasing, continuous, or maybe just even smooth. And it's equal to 0 if t is bigger than 1. Okay? And we choose the weights to be eta epsilon of distance between x and y, where this eta epsilon is 1 over epsilon to the d, eta of t over epsilon. Okay. So you connect points that are on some length scale distance epsilon apart, And you could choose a kernel that's maybe just all ones and jumps to 0. I assumed it was smooth here, but you can easily relax this kind of thing. Or you can have some Gaussian kernel or something that you chop off at some point. So epsilon is a positive parameter. And then you can write down, say the graph Laplacian problem. But here, let's normalize the graph Laplacian the right way. So I'll call it L and epsilon u of x. So the right normalization is to put a 2 over, I'll call this thing sigma eta n times epsilon squared, sum over my random variables. And it's eta epsilon of xi minus x, and then u of xi minus u of x. Okay, so this is my normalized graph Laplacian, the sigma eta. So we'll see in a sec that this normalization means that we're exactly consistent with a nice operator in the limit without having to change constants or anything. So this is the second moment of the kernel, dz. And this is the only way that the choice of the kernel comes into anything, is with this constant. Okay, so one of the oldest tools in numerical analysis to prove convergence of numerical schemes is the maximum principle, right? You have elliptic PDE on a grid, but it works on a graph as well. If you have the maximum principle and you have that the operator is consistent with an elliptic operator, you can prove convergence with a rate with a simple maximum principle argument. So let me just prove the pointwise consistency for the operator and then see how much time is left at that point.
I have a dumb question. Is set G included in that sum over all these lines, whatever?
The x here.
Yeah,
Or,
the value that you're given is in there somewhere. Those are in the inequality, in the minimization, in the original minimization. Sorry.
in this thing,
Yeah.
is the g included in this sum?
Yeah.
It doesn't matter so much. You can pull those terms off if you like, right? And the way I've written it, yes, yeah, yeah. So you have some terms that have a u of x and a g of y or something, right?
Yeah.
Yeah, exactly.
A question.
Yeah.
I know you're talking about the big data limit, but this will work with small data too. Like you don't have a lot of information. Does it work? Does it propagate?
So it's the big data limit, I should say, in the unlabeled data. Okay.
Yeah.
But the question that you can ask is how big should this labeled data set be so that I get a nice continuum limit? And that's actually a fairly hard question. This is something that we've been addressing recently, and our preprint is almost finished, let's say.
Totally different question.
Yeah.
On a practical level, if you don't have a lot of unlabeled data,
Yeah.
can you still does it work?
So the point of this is to use an abundant amount of unlabeled data in the learning. If you don't have a bunch of unlabeled data and you don't have any labeled data, then you don't have anything, I guess. But if you don't have a bunch of access to a bunch of unlabeled data, maybe you shouldn't use semi-supervised learning. Yeah.
You can use the graph.
I mean, the graph is constructed on the unlabeled data plus the labeled data, so it's the union of these two things. But usually usually the idea you have in mind is that you have a very small amount of labeled data and a large amount of unlabeled data. If you have lots of labeled data, you should just use like deep learning or something. You shouldn't need to use the properties of the unlabeled data. Okay. But we're just going to look for the moment that if I ignore the labeled data and just look at the consistency for this operator. Okay. So let's do it in two steps. And so essentially, there's one small point, which is that this x, usually people take it to be in your data set, but actually you can just take it to be anything you like in your domain. And this is it's a well-defined random variable. So the first theorem. Essentially, let's write down a non-local operator, 1 over integral over omega of beta epsilon x minus y rho y dy. Okay. So the first theorem is that I have consistency to the non-local operator, so L of u. So for anything in C3, actually, this just needs u to be Lipschitz, I guess. Okay. So less than equal to essentially lambda with probability greater than 1 minus a constant exponential. Actually, it would just be 2 here, let's say, minus a constant and epsilon to the d lambda squared, d plus 2. So in all these kinds of results, you pass from discrete to non-local, and then you Taylor expand, pass from non-local to local. Right? So the proof of this is an application of Bernstein. And here, it really matters that you use Bernstein and not Hoeffding, let's say. Okay, so the variance of these random variables is much smaller than their absolute bound. So we're going to use Bernstein. And the random variables are over here, right? It's just everything inside the sum except for the 1 over n. So it's 2 over sigma eta epsilon squared, eta epsilon, and u si minus u of x. So I have these random variables, and the thing I'm looking at here is just 1 over n times the sum of these things. Okay? Now, what is the absolute bound I can place on these guys? Okay. I can say that, okay, so this eta epsilon has hidden a 1 over epsilon to the d in it, right? And then here, if u is Lipschitz, I get an epsilon from here, and I get a 1 over epsilon squared. So it's like a constant epsilon to the minus d minus 1. Right? This. And that's my b from Bernstein. Just to make sure it's right. This is the epsilon to the minus d. That's minus 2, but I get an extra epsilon from this, so it's minus 1. Okay. But what's the variance of the yi's? Okay, so with all these things, I'm getting rid of the minus the mean because that just gives me a smaller value here. So I can get rid of, if I look at the variance, it's the integral over the domain. It's basically this thing squared times rho. Okay. U of n minus u of x. So this whole thing squared and then times rho. This is an upper bound. Right? Okay. And if I see how big everything is, right? When I square this stuff, I'm going to get a constant epsilon to the minus. So here epsilon squared, that gives me a 1 over epsilon as well. And I'm squaring it. So it's like epsilon to the minus 2 from this and from that. And I get epsilon to the minus d from this thing, right? Actually, I have 2 copies of this. So one of them I'll pull out to epsilon to the minus d, and one of them, it's the integral over the ball of this guy. And that integrates to 1 because of the way that I've scaled the kernel. Okay. So I get c epsilon to the minus 2 minus d. Right. Did I do something? Oh, right. This is fine. Yeah. The point is, like, the variance is like a squared quantity. So if you take a square root, this is much smaller than the absolute bound. Right? So you should be looking at b squared and comparing against the variance. And when you have the variance is much smaller than b squared, that's where you want to use Bernstein. Okay, so I have these 2 things. That's sigma squared. And now Bernstein says that probability that Ln epsilon minus L epsilon u is bigger than t, let's say, is less than 2 exponential of minus nt squared. And now here you have sigma squared, so let's just put a constant down here. The sigma squared is epsilon to the minus 2 minus d, and the b is minus d minus 1. Okay, and there's also a t down there, and it's divided by 3, but I can pull out the divided by 3 into a constant, let's say. So I get this. Bring up the epsilon to the d plus 2, so minus n epsilon to the d plus 2 times t squared. And basically it's divided by c1 plus t times epsilon, right? And now I just have to restrict, let's say if I restrict t to be less than epsilon inverse or something, then this reduces to what I have here. So this is for lambda less than epsilon inverse. Okay. Make sense?
So the continuum limit is a non-local operator.
If you fix epsilon, yeah. So we're taking the limit as n goes to infinity, epsilon goes to 0. You could leave epsilon fixed, but the graph becomes non-sparse in this limit. So you really want to take epsilon to 0 to make the graph sparse as well.
And then you get a line.
Yeah, yeah. So that's the other thing that I'll do here is to see what the Laplacian is. So now that I have a non-local operator, I can forget about probability. I can just Taylor expand and see what I get here for the asymptotics, right? Sorry, I used lambda, but I used t later, so this is really the same t before. Yeah. Okay. So just to point out, what do you need to have consistency? This already gives you a condition on the length scale, because you want this to be a small probability over here. If you want it to be a small probability for t being less than 1, right, then this quantity here has to be large. Okay? So you get a condition automatically that n epsilon to the d plus 2, actually you're going to have to union bound over the whole point cloud, so this is going to have to be at least as big as, or much bigger than log n in the end. And so this turns into a length scale restriction that epsilon is much bigger than log n over n to the 1 over d plus 2. Okay? So you immediately get this kind of lower bound length scale restriction for epsilon if you want to have consistency even to non-local operators.
Wait, sorry, why is that a need?
Well, if you want this to be a small probability, and t, you don't want to take t too small. I didn't say where that comes from, but you have to apply this to every point in the point cloud. There are n points. So I use the union bound, I get an extra n here. I bring it up here, it becomes plus log n. Okay. Yeah. But let's look at the asymptotics for the operator. So if I just Taylor expand, I'll just do a simple argument for a smooth function u. It's just epsilon squared, right? Yeah. So it's really integral over a ball. And we'll assume that the ball is contained entirely inside our domain. If you want to do this all the way up to the boundary, you get a whole bunch of extra annoying boundary terms I don't want to worry about. So you get eta epsilon x minus y. And if I Taylor expand u of x minus u of y, well, I'm going to have grad u of x dotted with y minus x plus a half times y minus x. Or, you know what, maybe I should do a change of variables first to make this easier. Let's do that. So rho of y. Now make a change of variables so that z is equal to y minus x over epsilon. Okay. So now it's the integral over the unit ball here. It's eta of z. So in the eta epsilon, I have a 1 over epsilon to the d, which cancels out the change of variables. dz is equal to 1 over epsilon to the d dy. Okay, so that gets absorbed into the constant in eta epsilon, and it becomes eta of z and u of x plus epsilon z minus u of x. And here I have rho of x plus epsilon z dz. Okay. And then I'm going to, now it's a bit easier now to Taylor expand. So eta of z And here it's going to be grad u of x dotted with epsilon z plus a half epsilon squared z transpose the Hessian of u z plus order epsilon cubed. Okay. And then times for rho, I'm going to have rho of x plus order epsilon and then dz. Right? Sorry, this is annoying. I have to also expand all the way out to the first order terms here. Rho of x plus grad rho of x dot epsilon z plus order epsilon squared. Okay. It gets a little messy. So the point is that I have a 1 over epsilon squared here, so I can only deal with order epsilon cubed error terms inside the integral. Okay? So I have to keep the first order ones in rho and the second order terms in the Hessian. Now what do I have if I just combine all the terms that matter here? So I'm going to have 1 over sigma eta epsilon squared. Let's see. So the first thing is I'm going to have, if I have rho of x times this, okay, that integrates to 0 because it's an odd function. So that guy's gone. Then I have rho of x times this. So let's write that down. It's going to be a half. The epsilon squareds will cancel, right? I'll get a 1 over 2. And did I forget to put the 2? Yeah, in here I had a 2, and here I didn't. So really I had a 2 here all along. And it was there to cancel the 2 that was sitting here. So anyways, 2, 2, and 2. So you get z transpose, Hessian of u and z. And then I have, now this hits the order epsilon cubed, but that's gone. Now over here, when this multiplies that, I get something that's I have to record. But when this multiplies here or further on, I get epsilon cubed. So I have one more term that looks like these two multiplied together. So I get, there's a 1 here, 1 over that, and then plus, now it's 2 over sigma eta. The epsilon squareds cancel as before. 0, 1, eta z. And you get this thing that looks like grad u of x dotted with z grad rho of x dotted with z. Okay. And then plus order epsilon cubed. Or order, now it's order epsilon. I divide by the epsilon squared. This thing, right? Yeah, sorry. Yeah, sorry, I had that floating around still, right? Yeah, rho of x. Yeah, thank you. Okay. And now let's simplify this. So rho of x over sigma eta. Now I'll just pull the sum outside. That defines the quadratic form here. And it's going to be u xi xj at x, and then integral of eta of z, and then zi zj. All right, that's the first term. And same kind of thing for the second term. I have two sums here. I can pull it out into a double sum. It's 2 over sigma eta. And it's u xi rho xj. And then it's the same kind of integral. Eta of z, zi zj dz over the ball plus order epsilon. Okay. And now you just note, right, if I is not equal to j, it's an odd function again, and these things drop out. Okay? So you get just the diagonal terms in the sum. So you get Laplacian here, and the diagonal terms here give you the dot product of grad u with grad rho. You get rho of x over sigma eta, and you get, okay, and so the diagonal terms have a zi squared, and it's the same constant for all the i's. It's the sigma eta I wrote earlier. Okay? So you get sigma eta times Laplacian of u. These guys drop out. And then you get plus, and over here, again, it's the same thing, sigma eta. Okay? So you get 2 and grad u of x dotted with grad rho of x. Okay? Plus order epsilon. So you have diffusion that depends on rho over here, and you have a drift term. Okay. But it's also useful to write this in divergence form. Okay. So here I've gotten, let's just record this guy, LU of x. L epsilon u of x is rho Laplacian u plus 2 grad u dotted with grad rho plus order epsilon. And now here, what do you do? So let's write this as rho inverse rho squared Laplace u plus 2 rho grad rho dot grad u. Okay. And this thing here is just exactly divergence of rho squared grad u. Okay, so this is a more useful way to write this sometimes. So you can think of it just as diffusion with a coefficient that's just rho squared. So you diffuse faster in dense regions and slower in sparse regions, which is basically this manifold or this semi-supervised smoothness assumption I talked about. You should propagate labels very smoothly, in high density regions, and you should not do this in low density regions. So there is, yeah. So what is this? If I just, this is equal to 0, so I can drop that if I like. And so this is just the Euler-Lagrange equation for the problem minimize integral of grad u rho squared dx. Okay. So this is the variational problem corresponding to this Euler-Lagrange equation. And so now from the variational point of view, why is it rho squared? I had a double sum in the energy. So you get expectation sort of twice. So you get times rho of x times rho of y, and you get a rho squared in the end. Okay. So this is like from the double sum that defines the energy, right? It's x and y, w x y, u of x minus u of y. Okay. Okay, so from this, you can immediately prove discrete to continuum convergence with rates, at least in simple settings. So let me just end with this. So say that we take our labeled points to be everything that's close to the boundary. So it's all the xi's such that distance xi to the boundary of my domain is less than epsilon. So I have a domain where I'm sampling the points. I take a tube around the boundary, order epsilon. Okay? And any points that happen to fall inside that tube, I assign the labels given by a smooth function g. Okay? So I have the discrete problem, ln epsilon u of x is 0 on the set, I'll call it x sub n for all of the points, minus gamma. And then u of x is equal to g on gamma. And I have the PDE, which is divergence rho squared grad u is equal to 0 in the domain, and u is equal to g on the boundary. Okay. So this is my discrete problem. This is my continuum problem. Okay? And this is enough data in this setting. Actually, you can make this narrower than epsilon, which I'll say in a sec. But this is enough to say, just with a simple maximum principle argument, that the solution here, right, call this u sub n, let's say. U sub n minus u is less than c times epsilon with probability bigger than 1 minus c n exponential minus n epsilon d plus 4. Okay. So you get order epsilon error estimates with high probability. Okay. And it's a direct application of the pointwise consistency we just proved with the maximum principle. Okay. You can look in the notes if you want to see the exact proof. The thing that's trickier is if you want to use fewer labels than this. So here I did everything in the order epsilon tube. We can make that much smaller. Actually, we can make that down to epsilon squared width. The reason you need order epsilon is because all of our pointwise consistency means requires the ball to be contained in the domain. Okay? So I don't want to overlap the boundary. Okay? But we can take this down to, this is the recent work, we can change this to a delta right here. And the error estimate becomes, say, this times epsilon over delta, essentially. Okay. You can take it all the way down to delta as small as epsilon squared before you lose the convergence rate. Okay. This is a lot harder to prove because you can't use pointwise consistency anymore because you go all the way up to the boundary, essentially. So this uses random walk arguments to prove this kind of thing. And okay, so I have 4 minutes to say something else. So let me lead into maybe the kind of thing that Diane is going to talk about tomorrow. So this is like the PDE perspective, right? You can use the consistency of the graph operator to a continuum operator plus some nice stability results like a maximum principle to get convergence. If the solutions are not smooth, right? So the reason you get the order epsilon rate here is that you can take the smooth solution of the PDE, restrict to the graph, and use the pointwise consistency. If you have the P Laplacian, let's say, where solutions are only C1 alpha, okay, then you have to use viscosity solution framework instead, but this is almost the same kind of thing because now you just restrict your smooth test functions to the graph and you evaluate them on the graph Laplacians, and you can push through all of the viscosity solution framework and get the same kinds of results, but you lose the convergence rates, so you just get uniform convergence with these things. So the maximum principle is great if you can use it. Okay, so if you have a Laplace equation or a P Laplace equation, then you have the maximum principle, you can use viscosity solutions, everything is great. But there's a whole host of problems where you can't use the maximum principle. And let me just mention some of them. So one thing I talked about Monday was that the spectrum of the graph Laplacian, so eigenvalue problems. Okay. Here in the continuum, everything's nice. I have smooth eigenfunctions and so on, but I don't have a maximum principle. I have no nice stability results for the equation. Solutions are not unique and so on. So the maximum principle doesn't work to give you convergence of eigenfunctions, let's say. So here you need a combination of variational and PDE tools. And this is really like gamma convergence kind of tools. And if you couple these with PDE tools, then actually we can prove, just in a recent paper, we proved the same order epsilon convergence rates for all the eigenfunctions if you combine these gamma convergence plus the pointwise consistency results. Okay. And the other ones are like graph cut or TV problems or total variation. So total variation corresponds sort of like the one Laplacian in the limit. And here you don't have unique viscosity solutions, you have maybe discontinuous solutions and so on, so you can't use the maximum principle, you can't use viscosity machinery, and so these are problems where you really, the tools that really shine are, again, the variational tools and gamma convergence. And so here the notion is different. You're not trying to look at pointwise consistency of the operator. You're looking at the energy itself, and you're seeing, can I take a function on the graph and can I extend to the continuum in a way that controls the continuum energy by the graph energy? And can I do it the opposite way? And if I can do this in both directions, I can get even convergence rates with variational tools. So I'll stop there.